So I'm going to share my screen now. Mayuri, can you please confirm if the slides are visible and I'm audible?
Yes.
Okay, so I'll start with the session now. So, good evening, everyone. Myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, and I welcome you all to the third live session of the NPTEL online course Basic Principles in Calculations in Chemical Engineering, course instructed by Professor S.K. Majumder from IIT Guwahati. So, let's get started. So, some information about these courses, not the course, these sessions, is that these sessions will be held every week on Tuesday from 7 to 9 p.m. The access of these live sessions recording have been shared with you, and you can also access it through my YouTube channel. The structure of these sessions will be first we will go through the overview of the lectures for the corresponding week, which is the third week for this time, and then we'll solve some sample problems related to your assignment, which will help you solve them. So, in lecture 7, we studied the principles of material balance and calculation. Um, in that, we firstly dealt with the process flow sheet or flow chart. So, it is basically a sequence of processes, basically organized together to give you a sense of how the material is flowing through the system. So, here, if you see the first figure given here, so here, this is an absorber stripper system. So absorber basically absorbs the gas from a mixture of gases, a particular gas. In this case, it may be CO2, and then H2 or H2S, and then the absorbed gas is then uh, absorbed gas into the liquid which is passed through it, and this whole liquid plus gas mixture is then passed through the stripper, through which we get the gas in the pure form. So this absorber stripper system is shown here. So this is basically a series of process, and this is the flow sheet that tells us which stream is doing what and how these processes are connecting. Um, so next we go to, this is another process flow sheet given here. So this is a reaction between hydrogen, and toluene, and this gives us benzene and methane. So these are the effluent coming out of this reactor, and the gas separator is here so that we can get the pure benzene and the mixed gases. And the unreacted reactants are then recycled back to the reactor through this separator, through this still, sorry. Um, so you can basically define your system as a one process unit or a multiple process units. So here this is a diagram for a one process unit shown here. This is basically a mixing tank. So stream 1 and stream 2, which has material A and B, uh, is flowing into this mixing tank, and another stream is coming out of it. So it's basically a mixed product. So this agitator helps in mixing the two streams. And another single process unit which I can show is the distillation. Uh, so this is the inlet stream, which is called the feed, and based on what is your desired product, if it is the distillate which comes out from the top of the distillation column, this will be your product, or the bottoms or the residue which comes out from the bottom of the column. So then we studied a bit about the general material balance equation. So what is the general material balance equation? So suppose you have a system. So this is a system. Yeah. So this is a system. This will be the input. This will be out. This will be the output. So these are the process. These are the streams which are flowing through the system. So this is the input and this is the output. If in the system a reaction is also occurring, so some in this system itself, something will be generated. Some material will be generated. It may not be the same material, and some material will be consumed. So suppose some reactants are flowing in, the reaction is occurring here, and the products as well as the unreacted reactant is coming out. So how to do the material balance across this system? So basically, we make this boundary, and something which is generated is inside the system, something which is consumed is also inside the system. Input is the input of the reactants, and all these things are flowing as the output. So it may be steady state or it may be unsteady state. If it is the unsteady state, so the input and output flow rate may not be the same. So some material may also get accumulated inside the system. So this is basically the general material balance equation. So accumulation within the defined system is equal to input through the system boundary minus output through the system boundary plus generation within the system and minus consumption within the system. So something like this. Um, So why these output and consumption are in having negative sign before them is because something is coming out of the system or something is getting reduced. I mean in the quantity. So that's why these are negative signs. And so if something is getting generated or produced or coming into the system has positive sign. So also, the material balance can be written in terms of the total overall mass or mole balance. So, if the inlet streams and the outlet streams are there, and there is some generation and consumption as well. But if you want the overall balance, so what will be the flow rates of this inlet and outlet stream? You can write the total overall mass or mole balance. Then mass or mole balance of each chemical compound or component material balance. Then mass or mole balance of an atomic species. So suppose you have some species CH4. So if you want the carbon balance, you can do that as well. Um, then the procedure for material balance equation was discussed. So here, if you see, this is these are the steps that you have to follow. So firstly, you are given some problem. So firstly, draw the flow chart and write all the given data. Then choose one stream as the basis. It can be inlet or outlet based on what is given, what are the known values that are given to you. Then convert the volumetric flow rates to mass or molar quantities because you have to do the material balance. So volumetric flow rates need to be converted to something which has mass or molar quantities. Then label the unknown streams. Uh, Label basically all the streams and give the labels for the unknown quantities as well. Then convert all quantities to one basis. means that if all the values, some of the values are given in on the on mass basis, and some are given in the mole basis, then convert it to just one basis. So all should be on the mass basis. If there are mass flow rate, then the fractions involved in the mixture would be mass fraction, not mole fraction. Please keep that in mind. If all the flow rates are in the molar flow rates, and then the fractions would be mole fractions. If some of them are in mass and some of them are in mass flow rates and some of them are mole flow rates, convert them accordingly to the just to the one basis. Then write material balance equation, maximum number of independent equation. Then solve the derived equation to get the unknowns. So we will look at how this is done for two examples. So this is the mixing tank, uh, and this, as you can see, this is the stream A, this is stream B. We have named these streams A, B, and C. Now this A stream has some concentration of acetic acid and some concentration of H2O, basically a mixture. And this is another mixture having 58% of acetic acid and 58% of H2O, so equal quantities. And then this is C stream, and this has 35% of acetic acid and 65% of water. So we will firstly write what are the unknowns here. Currently, what are the unknowns here? So we don't know what is A, B, C, X, or Y. So you can also write it in a way. So this is X of if let acetic acid be P and water be W. So X of P in A. Okay, and this is X of W in A. So this is basically the mass percentage or mass fraction of P in A. Now what would this be? X of P in B stream, and this will be X of W in B. Similarly, this will be mass fraction of P in C, and this will be X of W in C. So we have named all the quantities which are given here. Now, what are the unknowns here are A, B, C, X, and Y. So you can write it as what is X? Can somebody tell me what is X? X is X of P in A, and what is Y? It is X of W in A. Okay. So these are mass fractions. As you can see, all the units are consistent here. A is given in kg per hour, B is given in kg per hour, C is given in kg per hour. If all are mass flow rates, or as well as the concentration given here are in weight percent as well. So, or the mass percent as well. So we don't need to change anything here. However, there are some unknowns here. So firstly, we will write the overall material balance. It is abbreviated as OB. So overall material balance would be the so now as you can see, this is a steady state. It is given that it is a steady state operation, and we have the inlet and the outlet, and no reaction is taking place. So going back, so if it is a steady state operation, the accumulation term will be zero because the inlet and outlet flow rate are same, and there will be no accumulation within the system. Then and if there is no reaction also happening, then there will be no generation or no consumption. So, sorry, if we go for the uh, overall material balance, so we firstly write the general material balance equation. A is equal to I minus 0 plus G minus C. So here A is accumulation, I is input, O is output, plus G is generation, and minus C is consumption. So here if we see it, if it is a steady state, this will go to 0, this will go to 0, and this will also go to 0. Nothing is generated, nothing is being consumed, and accumulation is 0. So basically here input is equal to output. So, so if we see input is A and B and output is C. So we can write A plus B gives C. If we go for component material balance, for P, P is acetic acid. So if we go for that, so we have to equate the mass coming in of acetic acid to mass going out of acetic acid. So what would be the mass coming in through stream A? So that would be this is basically the mass fraction if you see. So XPA into A, then mass fraction of P in B into B, and then mass fraction of P in C into C. So this is how you do it. And if you want to compute what will be the XWA, another way you can write the component balance of that as well. But one more way to do is that, as you know, the sum of the mass fraction, all the mass fraction is 1. So as there are only two components, so 1 minus XPA will give you XWA. So now these are the two equations given to us. But there are more than two unknowns here. As you saw that there are 5 unknowns here. So what we can do is we can so we would need some basis, and it's not like that all of the values will be unknown. Some values will be given to you, and some values need to be given. So here we can say that A is 200 kg per hour, and the XPA is 15%. 15%, or you can write it as 0.15. Okay, 0.15. A is given, XPA is given, We are also given these things XPB, XWB, XPC, and XWC. So these are not the unknowns anymore, XPB, because these are given in the problem, XPB, XWB, XPC, and XWC. So if we put the values here, this becomes, 200 plus B is equal to C. And the bottom one becomes, so XP is given to us and A is also given to us. So 200 into 0.15 will be 30. Plus XPB. What is XPB? Can anybody tell me what is XPB? Kindly mute yourself if you don't have a question. Kindly mute yourself. Whoever is joined right now. Hello? Can you hear me? Kindly mute yourself. Mr. Shyam Kumar, can you mute yourself? Mr. Shyam Kumar, can you mute yourself? Can you hear me, Mr. Shyam Kumar? Shyam Kumar. Mr. Shyam Kumar, can you hear me? Mr. Shyam Kumar, can you hear me? So what would be XPB here? Can anybody tell me? All right, so XPB will be 0.5 into B equals XPC is 0.35 into C. So these are the two equations now. 30 plus B equals C, and 200 plus B equals C. Now that. And this is 30 plus 0.5 B equals 0.35 C. So if you solve, now you see that there are two unknowns here, B and C. So these are two simultaneous equations. If you solve them, you can get the answer for B and C. So so how to solve them is that you can substitute either the value of C. So C is 200 plus B. So 30 plus 0.5b, 0.35 into 200 plus b. So this will be 35 into 2 is 70, 70. So this will be 70 plus 0.35 b and 30 plus 0.5 b. So this becomes 40 and this will be 0.15. Sorry. So B will be 40 by 0.15. So how much would that be? Can anybody tell me what is 40 by 0.15? Anybody? Can somebody give me the answer? Okay, again no response. 266.67 kg per hour. So this is B. Now as you know this is B, so you can also compute C. So 200 plus 266.67 will give us C if you put the value of B here. So this will give us 466.67 kg per hour. Also, if we are given XPA 0.15, so what will be the value of XWA? Can somebody tell me what will be the value of XWA? Can somebody tell me the value of XWA, Mayuri? Okay, if you cannot, so basically in A has two components, P and W. So one of the mass fraction is 0.15. So the other will be 1 minus 0.15. So basically the mass fraction here is 0.85. So it's not an unknown basically if you know the one of the mass fraction of the same stream. Next we have a distillation column here. So a mixture of methyl alcohol and water is going in, and it has the inlet flow rate of 1000 kg per hour, and the distillate quantity is also given to us, which is 327 kg per hour, and the bottom quantity is also given to us, which is 673 kg per hour. We know the concentration in the distillate stream and the feed stream, but we don't know what would be the concentration of these components in the bottom stream. So how to find that out? So we'll do that here. So again, we'll firstly name these streams F, D, B, and these components concentration as X of M in F. This will be X of W in F. This will be X of M in D. This will be X of W in D. Now what we don't know is X of M in B, we don't know. X of uh, W in B we don't know. So how to get that? So firstly we'll write the overall balance. So what would be the overall balance? It is the inlet and outlet stream. So why inlet and outlet only and not generation and consumption? Because there is no reaction occurring here. Basically, we are just separating, we are enriching basically the two different streams. So this will be richer in the lighter component, which is methyl alcohol, and the bottoms will be richer in the water. So there is no reaction going in. This is just a unit operation, not a unit process. So what will be the overall balance? Inlet minus outlet only. And as this is the steady state. So we get that F is equal to, sorry, D plus B, because this is the stream coming in F, outlet streams are D and B from this system. Then the component balance for M, which is methyl alcohol. So what will be the component balance? Again the same thing, mass in minus mass in is equal to mass out. So mass in will be 0.5 into 1000, which is the value of F. So I'll just write what is given here. F is 1000 kg per hour. Then D is given to us 327 kg per hour. B is also given to us 673 kg per hour. Okay, and these are the values for the different mass fractions. So 0.5 will be XMF, XMF into F, giving XMD. So I'll write it here once. XMF into F is equal to XMD into D plus XMB into D. So 0.5 into 1000. So XMD is 0.96. 0.96 into what is D? It is given to us 327. But we don't know what is XMB. So we'll write the unknown here, XMB into B. B is given to us 673. Or even if it was not given to us, we can calculate it using this, because we know what is F and what is D, so we can readily calculate what is B. So only one unknown is here, XMB. So we only need to solve this equation only, because everything else is given, FDB is given. So if we solve this equation, this is 5,000, sorry, 500. This value will be 0.96 into 327. 327 is 313.92 plus XMB into 673. So XMB will be 500 minus 313.92 upon 673. So XMB, we get it as 0.276 roughly. So and what would be XWB? Again the same thing, 1 minus xmb, which is 1 minus 0.276. So 0.724. So this is how you compute what are the mass fraction in the outlet stream of the bottoms. So we now move to the lecture 8. It dealt with the material balances on processes with recycle and bypass. So what is recycle? Recycle is shown in this figure. So here this is the process unit. Something is coming in and something is coming out. However, this is the fresh feed, and from here whatever the effluent from the reactor is coming out, it is going through a separator, and this separates the unreacted reactant and sends it back to the and joins it with the fresh feed. So this is basically the process feed, which is also called the mixed feed. So it has the recycled reactant and the fresh feed, which gives us the process feed, which comes goes into the process unit or the reactor. And these effluents which are coming out of the reactor, this may also again have the unreacted reactant which goes through the separator. We get the net product, and this is the most of the unreacted reactant is separated through and then recycled again. So this cycle continues. This is the recycle, basically used to increase the efficiency of a system, so that whatever the unused reactant is coming out from the reactor is used again and again. Then what is bypass? So this figure shows the bypass system. So bypass is basically there is some fresh feed coming in, but there is we divert this stream. Some of the part of the stream is diverted. So basically, and then add it later uh, to the reactor effluent. So basically, some reactant is diverted from this process system, bypassing this system. It is not, some part of the reactant is not going into this process unit. So it can be used basically to control the process flow rate, to control the level in the reactor as well. Then purge. What is purge? So purge is shown through using this figure. So this, as we know, is the recycle system. And again, using this separator, we get the unreacted reactant. As well as it might be that we may not have a very pure reactant coming in, it may have some inerts as well. So if we keep on recycling unreacted reactant as well as the inerts may also get in. So the concentration of inerts inside this process unit may increase and increase and keep on increasing. So to avoid that, we put in a separator here and then remove the inerts through the purge stream. So this is the purge. And makeup, as you can see from this figure, is that when you recycle the reactant, you can add some more of the reactant through the makeup stream so as to maintain the flow rate inside coming into the reactor. So this figure shows you the overall how the process stream, different process streams are there. So a fresh feed, sorry. So a fresh feed may come in. Some of the feed may be bypassed over the system, so that some of the reactants don't really go into the system. Uh, then it goes through the reactor and then the separator. From the separator, one of the streams which has the pure reactant, some to some degree, to most of the degree basically, is then recycled back and added to the fresh feed. Some makeup can also be added there so as to maintain the flow rate, and to remove the inerts, this is the purge stream, and then we get the net product here. Next, material balances on reactive processes. So, firstly, it dealt with the stoichiometry. So, stoichiometry is basically the relation. between the concentration or the masses of the reactants and the products. Then next we saw the limiting reagent or the reactant. So this is the reaction given here. This is the reaction to form the ammonia. So here we see that 3 moles of hydrogen and 1 mole of nitrogen react to give us 2 moles of ammonia. So what if, and this is a balanced equation. So what if I have, suppose, 2 moles of hydrogen and 3 moles of ammonia. So would what would so which reactant may get consumed first? Because from here we see that for if we have some amount of H2, 1/3 of it amounts we need as nitrogen. So if this is twice of hydrogen, so 2 moles of hydrogen, so we would need 2/3 of nitrogen. So 2/3 of nitrogen will be 0.667 moles. So basically we have more of this nitrogen here. This nitrogen is in excess, so hydrogen will get consumed first. Basically it will be finished and we will remain with the unreacted nitrogen. And so basically in that case, if 3 moles of hydrogen gives us 2 moles of ammonia, so 2 moles will give us how many moles? If 3 gives us 2, so 1 will be giving us 2 by 3. And then 2 will give us 4 by 3 moles. So 4 by 3 moles of ammonia will be given, but we will be unreacted nitrogen will be 3 minus 2 by 3. So 3 minus 0.67. So that will be the unreacted amount. So this is basically nitrogen in excess, and hydrogen, it is the limiting reagent. And based on this limiting reagent, different other definitions are given here. So, so consider this reaction system. So A plus B giving C plus D. And then again with this C which is being formed reacts with B and gives us E plus D. So it is basically a series reaction in terms of C and a parallel reaction in terms of B. So this is a reaction system given here. So based on if suppose the limiting reagent is A, so the conversion of A is defined as the mole of A reacted upon mole of A fed. So what is mole of A reacted is that something A in, A out, and this is the system. So this is A coming in and this is A coming out, moles of A coming in, moles of A coming out. And in this system, the reaction of A is occurring. So what will be the mole of A reacted will be A in minus A out, correct? Because that's how much the amount of A is being consumed here. And upon mole of A fed will be A in. So this is the conversion of A. The selectivity of C. So suppose if there are C, D, and E, and we think that C is the desired product and E is the undesired product. So how can you define the selectivity of C? Is that moles of C in output upon moles of E in output. And if it was the selectivity of E, so this relation would be inversed. Then the yield of C can also be defined. So yield of C is basically how much of reactant are you putting in and how much of the product are you getting it with respect to that. So moles of C in output upon mole of A fed. Another term which is the efficiency in terms of the product C can be defined as mole C in output upon mole of A actually which are reacted, because some of A may also uh, 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 may be unreacted. No, it may not be unreacted, but actually which is being reacted to give us C. Next, the overall and single pass conversion. So here we can see that this is a reactor and there is one uh, uh, recycle stream above it, and then which is giving us the mixed stream here. So if we want a single pass conversion, it will be through this it will be across this unit reactor, and if we want an overall conversion, it will be considering the complete it will be considering the complete system including recycle stream. So the overall conversion of A will be for the whole process. So what is coming in and what is coming out. So 75 mole per hour of A is coming in. What is coming out for A? Only A. There is nothing of A here, so 0. And coming in is again 75. So we get 100% overall conversion of A if we see. But if we consider only this process unit and not the recycle stream, so here we see that 100 mole per hour of A is coming in, 25 mole per hour of A is going out, and coming in again is 100. So this will give us 75 by 100, 75% single pass conversion of A. So this is only across the reactor, not considering the recycle stream. Next, the extent of reaction was defined. So it is defined using this relation. So xi is the extent of reaction. So change in xi is change in moles for a particular species or a reactant upon the stoichiometric coefficient. So, and for equilibrium, it can be defined using this relation. So, whatever the moles are at the equilibrium minus the initial moles upon the stoichiometric coefficient. And for multiple reactions, the relation is given as such. This is the initial moles, and this is the stoichiometric coefficient for a particular species of the jth reaction. So, suppose there are reactions 1, 2, 3, 4, but there are multiple reactions, 3, 4 reactions. If there are 4 reactions, the J will be equal to 4, and this is the stoichiometric coefficient of the jth reaction, and this will be summed over. Next, material balances on combustion reactions was dealt with, and in that we saw the complete combustion, incomplete combustion, and excess air or excess O2. So suppose uh, you have a fuel and you burn it, basically that is what is called combustion. So burning or oxidation of some fuel is called combustion. So here suppose, and what are fuels? Basically they are hydrocarbons mostly. So here we see this is a hydrocarbon, this is propane. So propane, when you add oxygen to it, some amount of oxygen, you get, if it is a complete combustion, you get carbon dioxide and water. So what will be the value of XYZ here? Can somebody tell me? Can somebody tell me what will be the value here? What will be the value of XYZ? At least tell me the value of Y. So if you look at the left hand side, C is 3. So here to balance it, Y will be 3. No, it will be 3. It will not be 6. Value of Y will be 3 because we need to balance the carbon here. So Y will be 3. Now what will be the value of Z? As it is 8 here and already we have H2. So this will be 4 into 2. So Z will be 4. We need to balance whatever H is here. So H is 8 times. So this will be 4 into 2 H again 8 times. So this is 3 and 4. So firstly you get the amount moles of CO2. So 3 moles of CO2 we get and 4 moles of H2O. Now we know what are the moles of oxygen from here. So 3 into O2. So 6 here and 4 into O. So 4 here. So 6 plus 4 will give us 10 and we already have O2 here. So what will give us the 10 O is 5 here. So X will be 5. So this is what the answer is. So propane, 1 mole of propane requires for complete combustion 5 moles of oxygen, which gives us 3 moles of carbon dioxide and 4 moles of hydrogen. What if there are 2 moles of propane? Then you would require 10 moles of oxygen for complete combustion. However, what if you don't have enough oxygen? Then it leads to incomplete combustion. So this is the example for, or I can disconnect it, incomplete combustion. So this gives us carbon monoxide and water. And then the concept of excess air or excess O2. So for combustion, you may supply air or oxygen because air also contains 21% O2. So for combustion, you may supply air or oxygen. So it may be excess air or excess O2. So if you have, suppose for 2 moles of propane, if you supply 12 moles of oxygen, the required are only 10. So excess will be 12 upon 10 by 10 into 100. So 2 by 10 into 100. So that will be 20% excess, right? So that's how you can calculate. Firstly, you need to have a stoichiometric equation. If you have that stoichiometric equation and you have what is given to you, whatever the moles are of O2 or air are coming in, if you are given the moles of air, you can convert it to moles of O2. Okay, and then you can find out the excess O2, or directly you can also compute the excess air as well. Now we start with the sample problems. So first question is, for a steady state process with chemical reaction, a general material balance equation is, it's a steady state process. So I'll write the general material balance equation. A is equal to I minus 0 plus G minus C. So this is the general material balance equation. If we have a steady state process, this will be 0. But we have a chemical reaction. So something will also get generated and something will also get consumed. So these terms will remain. Also, it is a steady state process, so something will be coming in, something will be going out. So this will also remain and this will also remain. So the correct answer here is 0 is equal to input minus output plus generation minus consumption. I need a specific answer. I don't need the general material balance equation because it is given here steady state process. So the correct answer will be C.
Can you repeat
What part?
this? Why you taking this zero?
So uh, what is accumulation? So suppose this is a system. So this is the inlet stream, this is the outlet stream. So if the flow rate, if this is an unsteady state process, the flow rate of the inlet and outlet may not be the same. Due to some conditions, the inlet and the outlet flow rate may not be same. So if the inlet is not equal to the outlet, some material will be accumulated inside. So that is the accumulation term. So for the steady state process, the inlet is equal to outlet. So inlet flow rate is equal to the outlet flow rate. So that is how we get accumulation is equal to 0. Did you get it? For
Yeah, thank you.
steady state process. Yeah. Okay. So this is how you get it. Now, the significance of the recycle stream in a chemical process is to, so what is the main significance of the recycle stream? Can somebody give me the answer? What would be the correct answer here? We have just studied this. So the significance of the recycle stream would not be basically to add the inerts to increase the temperature of the system. This is not the correct answer. Or to remove the product to increase the separation or remove accumulation of unwanted inerts of material. The correct answer here is reuse the unreacted reactants. So as you see, some separator is given here. This is the reactor. So this will give us the unreacted reactant. So this is the fresh feed, this is the mixed feed, this is the effluent, and this is the net product. So if we keep on separating the unreacted reactant and putting it back into and add it to the fresh feed, this is basically recycle stream. So from the downstream stream, we are adding this unreacted reactant in the upstream stream. So the correct answer is reuse unreacted reactants. The third question, for the given system, overall mass balance can be expressed as. So this is the system as we have studied earlier. So these are the two inlet streams. This is the outlet stream. If this is a steady state again. So what will be the overall mass balance? So as you know, here from the general material balance, we can say if steady state accumulation 0, input minus output plus G minus P. So if there is no reaction occurring here, this is just a mixing system, okay? So this is 0 again because nothing is getting generated. No new product is being formed or some reactant is being consumed. So these will be 0, again accumulation 0 because steady state. So inlet is equal to outlet, okay? So what streams are coming in? A, then plus B is equal to C. So the correct answer here will be C is equal to B plus A. Next, the inlet of a distillation column has a flow rate of 100 kg per hour of a mixture of toluene and benzene. If the mass fraction of toluene is 0.4, how much benzene in the mixture would be coming in for a 1 hour operation? So if we take the basis as 1 hour operation, so we firstly draw the distillation column. This is the feed, distillate will be coming out. This is the bottoms. So the flow rate is given us here. So for 1 hour, 100 kg will be coming in. 100 kg of feed, and feed has a mix. Feed is basically a mixture. So mixture has toluene and benzene. So mass fraction of toluene is given to us. What will be the mass fraction of benzene in feed? Because that is what we need to calculate. How much would be coming in for a 1 hour operation? What would be the answer here? What will be the XBF? We don't really need to do the material balance across the system. This is just the summation of mass fraction. So we know that summation of all the mass fraction of all the components of a mixture gives us 1. So we know XT, because there are only two components here in the feed, XTF plus XBF. So this is mass fraction of benzene in feed. This is mass fraction of toluene in feed. Will give us 1. So we know what is XTF. So 1 minus 0.4 will give us XBF, which is 0.6. So this is the mass fraction of benzene in the feed. So how much benzene will be coming in? We know mass fraction. We know the feed mass as well. So sorry. So weight of benzene in feed will be X. Weight or mass of benzene will in feed will be XBF into F. So that will be 0.6 into 100. So that will give us 60 kg. All right. Next, match the following. Here I is equal to input, O is equal to output, G is equal to generation, C is equal to consumption, and A is equal to accumulation. So we need to match with the correct answers. So steady state with reaction. We have done this, I guess. What will be the correct answer here? Can somebody tell me? What will be the correct answer here? That's okay. Steady state with reaction will be the second option. Because again, accumulation term 0, reaction is there, so generation and consumption term will be there, and input and output terms will
First,
also be there.
first,
No, it will be second. Steady state with reaction. So accumulation term will be 0. Second option will be there. Steady state with reaction. Now give me the general material balance equation. What will be the correct answer here? General material balance. There is no constraint of steady state, unsteady state, reaction is there or not. So what will be the general?
output, third,
No, no, no. General material balance. There is no constraint. No constraint if it is steady or unsteady. reaction is there or not. What will be the general material balance equation? We have discussed this. It will be the first option. Next, unsteady state without reaction. What will be the correct answer here? Unsteady state without reaction. Something is getting accumulated because it is unsteady state. So the correct answer here will be fourth. And then lastly, steady state without reaction will be again accumulation term is not there, reaction is also not there. So G and C term will also be not there. So 0 is equal to input minus output or I is equal to output. All right. The correct option will be A2, B1, C4, D3. A2, B1, C4, D3. But sixth question, what is the makeup stream here? Can somebody give me the answer here? Makeup stream. So these streams are numbered as, so this is stream 1, this is stream 2, this is stream 3, this is 4, 5 and 6. What will be the correct answer here for the makeup stream? All right. As I had told you, makeup is basically to maintain the flow rate coming into the reactor. So this is the this stream here is the makeup stream. So 6 is the answer here. You add on to something which is coming into the reactor. So this is makeup stream. What is the bypass stream here?
Two.
Yes, correct. So you are basically bypassing it. This is some part of this stream 1 is not flowing through this reactor. You are bypassing it. It's flowing over the reactor if you go by this schematic, or it is bypassing this reactor and separator and joining stream 3 here. So this is the bypass stream. So C option. Now what will be the purge stream here?
Five. Sorry, six.
No, 6 we have done. 6 is the makeup stream. It is coming in. You see the arrow is inwards. What will be the purge stream?
It's five.
No, it's not 5. 5 is the recycle stream. See, separator, then some it is going back to the reactor. So 5 and 6 is adding up to it. So this is 5 is the recycle stream and 4 is the purge stream. Purge, as I told you, we need to remove some of is used to remove some amount of the inerts. One of the example is to remove some amount of the inerts from the unreacted reactant stream, so that the accumulation of inerts inside the reactor doesn't take place. So you are separating some unwanted components from your unreacted reactant, which is taken out from the separator. So fourth is the purge stream. Next, input and generation are two negative contributions to the system. Is this false or true? Input and generation. This is false basically. So if you go by the convention, when we write the general material balance equation, A is equal to I minus 0 plus G minus C. So I minus O, not 0. I minus O. So O is output, C is consumption. So I is input. So I has plus sign before it, and G also has plus sign before it. So these are positive contributions to the systems. Input, that something is coming inside the system. Generation, something is getting formed within the system. So this is this statement is false. The feed, next question, the feed of 100 kilomole per hour containing 40 mole percent benzene is fed to the distillation column. A distillate containing 90 mole percent benzene and a bottom product containing 85 mole percent toluene is to be obtained. Calculate the amount of distillate obtained. Now, from this question, we can firstly draw the flow sheet, and distillation column basically has three streams. This is feed, this is distillate, this is B. We are not considering the reflux here as it is not required in the question. So this is the distillate, this is bottom. Now we know the inlet feed is 100 kilomole per hour. Distillate amount we need to calculate. So D we don't know. But we know what is the concentration of benzene in the distillate. So distillate has 90 mole percent, or we can write as X X small b in D as 0.9. Now this feed has a mixture of, basically, as you can make out from the question, feed has benzene plus toluene in it. So some portion of benzene will be there, some portion of toluene will be there. So XBF and XWF. So XBF will be, from the question we can write it as 0.4. All right, and then automatically what will be XTF, sorry, toluene is there. So XTF will be 1 minus 0.4, 0.6. Please keep in mind that the units are consistent. So if the flow rates are given in molar form, it is given in kilomole per hour. All the other flow rates should be in the same unit, and the concentration are also expressed in the mole percent only, not mass percent or weight percent. If it is given in that way, in that form, convert it first. So XTF will be 0.6. So now here what will be the XBD? It will be 1 minus 0.9, so 0.1. And then what will be here? We know what is XTD, XTB, sorry. So XTB we know. So XTB will be, from the question, 0.85. And X small b, X of benzene in bottoms, will be 1 minus 0.85. That will be 0.15. Now we need to calculate the amount of distillate obtained. We don't know what is B. We don't know what is D. We only know what is the flow rate coming in. And the other concentrations are also known. So we will write the overall material balance. So firstly, I'll write the general material balance equation. A, just to make you understand. So again, this is a steady state operation. It is not mentioned anywhere it is unsteady, so this will be steady state operation. So accumulation will be 0. Distillation is a unit operation. No chemical change take place. It is a physical change taking place. The separation of two liquids. So generation will be zero, consumption will be zero. So again, we get input is equal to output. So we write the overall material balance equation here. So that will be, as we have named the stream, feed is equal to distillate D plus bottoms. Okay, distillate is D and bottoms is B. So we know feed is 100 kilomole per hour, or for 1 hour operation it is 100 kilomoles, and D and B we don't know yet. Alright, then we write the component material balance. I'll write it preferably for benzene. So what will be the component material balance equation here? So for benzene it will be mass of benzene in is equal to mass of benzene out. So mass of benzene in will be XBF into F is equal to XBD into D plus XBB into B. So this will give us the mass of benzene in distillate, mass of benzene in bottoms, and we add it and equate it to mass of benzene in feed. So we know some of these values, we'll put that here. So XBF we know, so 0.4 into 100 is equal to XBD we know, 0.9 into D plus XBB we also know, that will be 0.15 into B. We still don't know what is D and B. So these are the two equations which we need to solve. So now here we see that we have two unknowns and two equations. So we can solve this. So we can put in the value of B here. It will be 100 minus D. We can substitute that value here. So 0.4 into 100 will be 40. Sorry. 40 is equal to 0.9 D plus 0.15. We substitute the value of B here. 100 minus D. So it will be 15 minus 0.51 D, 0.15 D, zero point 0.9 D plus 40. So 40 minus 15 will give us 25, and zero point 0.9 minus 0.15 will give us 0.75 D. So D comes out to be 25 by 0.75. So it will give us 100 by 3, 33.33 kilomole per hour, as that is what the inlet feed stream's unit is. So 33.33 kilomole per hour. That will be the correct answer here. Next question. The reaction A plus 2B, A giving 2B plus C, sorry, takes place in a reactor. Refer the figure. The reactor effluent, it is named as E stream, is sent to the separator. So this is the separator. The overall conversion of A is 99. So the overall conversion of A is given. So we have studied this concept. The product stream from the separator consists of B, C and 0.2% of A entering the separator. So product stream is P, and it has some quantity of B, C and has 0.2% of A entering the separator. So 0.2 of A entering the separator. So whatever A is coming in the separator, 0.2% of A is here in this product stream. All right. So while the recycled stream consists of the remainder of unreacted A. So if this is as 0.2%, So this will have 99.8%, right? Entering this recycle stream R will have 99.8% of A, whatever A is entering in E. Now, and 1% of B entering the separator. So some B part also will be here. Part of B will also be here. Now calculate the percent conversion of A in the reactor. So basically we need to find out the single pass conversion across this reactor. We know the overall conversion. So that will be, so none of A is coming out from here. So what will be the overall conversion? So N of A in F, so moles of A in F minus N of A in P. I have named these streams here, upon N of A in F into 100. All right. So N of A in, so we know what is N of A in F. Do we know it? No, we don't know. So we take the basis as fresh feed entering is, we take a basis. If we don't know anything, we take the basis as 100 mole per hour of A in F. So this is fresh feed, so all of it will be A. So 100 mole per hour of A in F. So NAF will be in 1 hour operation 100. Now this we don't know, NAP upon 100 into 100. So this will get cancelled. This will be equated to the overall conversion which is given here. So this will be 99. So we can get the moles of A in product. So that will be 100 minus 99. So that will be 1 mole, or the flow rate will be 1 mole per hour. So 1 mole. So that will be NAP. Now we are given that NAP is equal to 0.2%. 0.2 by 100 into N of A in the effluent. Entering the separator is the effluent stream, right? So N of A in E, that 0.2% is NA of P. Okay. So from here we can find out NAE. So NAP is 1 into 100 by 0.2. So this will give us 2, then 10 here, 1000 by 2, 500. 500 moles. All right. So now 500 moles of A of obviously, because this is NAE. Now E is 500 moles, and this has 1 mole coming out of A. So rest will be in the recycle stream as given in the question, while the recycle stream consists of the remainder of unreacted A. So NA in R will be 500 minus 1, 499 moles. All right. And then this reactant recycle stream is being added to the fresh stream. So now what will be the Na in M? That will be the sum of Na in F plus Na in R. So that will be 100 is coming in Na in F, correct? This will be Na in F. So 100 plus 499. So that will be 599. All right. So what for the single pass conversion, we required Na in M minus Na in E upon Na in M. This will be the single pass conversion because the A coming in this reactor, this will be the across this boundary because we need to calculate the single pass conversion of the reactor. So NaM and the out will be NaE and input minus output upon input. So Na in M is 599 minus NaE is, what is NaE? It is 500 upon again inlet NaM 599. So this will give us the answer as 16.53%. 99 by 599 we need to calculate into 100. So it comes out as 16.527, so roughly 16.53. So this is the correct answer here. Oh, my bad. The correct answer here is 16.53. This 19.8 comes in if you put in 500 as here, which will be the incorrect answer. 99 by 500. That will be the incorrect answer. All right. So correct answer is 16.53%. Now next question. Excess reactant for a complete reaction is defined as. What will be the correct answer here? What will be the correct answer here? Excess reactant for a complete reaction is defined as. So it will obviously not be the reactant that would be depleted first. If we have an excess reactant, so that means we will have a limiting reactant as well. And limiting reactant is that which get depleted first. So it will not be this answer. Next, the reactant that will be last depleted. Yeah, this is correct. And also, if you look at this point, the reactant that would be most depleted. No, most depleted would be the limiting reactant. So this will also not be the answer. So correct answer is B. Next question. For an elementary reaction, uh, giving 5A plus 3B, for an elementary reaction of 5A plus 3B giving C plus 2D, 2 gram mole of A, 1 gram mole of B fed initially in the reactor and 1 gram mole of C and 2 gram mole of D is obtained at equilibrium. Nu I is the stoichiometric number of the ith species in a reaction. What is the value of nu A? So if we go by the convention, nu A, so stoichiometric coefficient according to this reaction of A will be 5. However, we need to consider the sign convention here as well. So for reactant, it is negative, and product, it is positive. So the stoichiometric coefficient here will be -5 for A. The correct answer is -5. We need to match the following now. So this is the reaction system, A giving P and A giving R. So this is basically a parallel reaction giving some uh, product P and also giving some product R. So selectivity of selectivity of P. So what will be the correct answer here? The correct answer here will be selectivity of P will be the moles of P, which is desired here as per this point, upon moles of undesired product if it is R. So moles of P in output upon moles of R in output. So fourth option here. Next, yield of P. So now we need to compute yield of P. So yield of P will be the moles of P in the output upon how much A is being fed. So that will be first option, first part here on the right side. Then selectivity of R, it will be basically the inverse of whatever was the A part. So that will be the second option, moles of R in output upon moles of P in output. Then efficiency of R production, that will be moles of R in output upon moles of A reacted. So the correct answer here will be A4, B1, C2 and D3. A4, B1, C2, D3. Okay. Next question. The stoichiometric coefficient will be treated as negative for reactant and positive for the product. Is this statement true or false? So we have discussed this. So this is the correct statement. So answer is true. Next question. For the reaction A plus B reversible reaction giving C plus D, 1 mole of A reacts with 1 mole of B to form 0.1 mole of C and 0.1 mole of D. What will be the value of the equilibrium constant? So we write the equation here A plus B giving C plus D. Now at time t is equal to 0, it is 1 mole of A and 1 mole of B, 0 moles of C and 0 moles of D. At time t is equal to equilibrium, we can say that zero point 0.1 mole of C is getting formed and 0.1 mole of D is getting formed. So if this amount of C is getting formed, and from this equation we can see that the stoichiometry is 1 mole for each product or reactant. So if 0.1 mole of A is getting depleted, so 0.1 mole of C is getting formed, and with it reacts with 0.1 mole of B to give D as well. So 1 minus zero point 0.1 here, and here also 1 minus zero point 0.1. Alright, so if we calculate the total moles here, 1 plus 1 will be 2. Again, 1 minus zero point 0.1 plus 1 minus zero point 0.1 plus zero point 0.1 plus zero point 0.1. So minus minus plus plus, all zero point 0.1 gets subtracted and 1 plus 1 we get 2 again. So total moles is 2. That remains intact throughout the reaction. Okay. Now we need to compute the equilibrium constant. So that will be fraction of uh, mole fraction of C into mole fraction of D upon mole fraction of A into mole fraction of B. So how do you get x of C? So x of C will be zero point 0.1 by zero point 0.2. So these are total. This is the moles of C at equilibrium, zero point 0.1, and total moles are 2. So mole fraction of C will be 0 0.1 by 2. Same goes for x of D, mole fraction of D, 0 0.1 by 2. Then x of A, 1 minus zero point 0.1, that is 0 0.9 by 2, and x of B again 0 0.9 by 2. So we put that here. So this is the mole fraction. These are the moles. 0 0.9, 0 0.9, 0 0.1, 0 0.1. And mole fraction will be dividing by total moles. Keep that in mind. If you are asked what are the moles, and or whether you are asked what is the mole fraction. So xc will be 0 0.1 by 2 square into 0.1, sorry, xc will be 0.1 by 2 raised to power 1. Sorry, no stoichiometric coefficient there as such. And then xd will be 0.1 by 2, xa will be 0.9 by 2, and XB will be, sorry again, 0.9 by 2. Sorry. So these two will get cancelled. We'll get 0.1 by 0.9 square, 0.1 square by 0.9 square. This comes out to be 1 by 81, which comes out to be 0.0123. So the correct answer here is 0.0123. Next question. The conversion of reactant A for the reaction A giving B is defined as. So the correct, we will define conversion of A. So moles of A reacted. So how many moles of A are getting converted to B? So moles of A reacted will give us B. So moles of A reacted upon moles of A fed. So is there some relation giving us that moles of A reacted upon moles of A fed? This will not be the correct answer. This will also be not be the correct answer because basically the inverse. This option here we can see 1 minus mole of A in output upon mole of A fed. So this will give us mole of A fed minus mole of A in output upon mole of A fed. If we simplify this, so mole of A fed minus mole of A in output is basically mole of A reacted. So this is the correct relation given here for the conversion of A. Now, next question. For a given parallel reaction, A giving B desired, A giving C undesired. So C is undesired, B is given, so it is desired. So the yield of B is given as, so we know the amount of B in output upon the moles of A fed. So this is the correct option here. Next question. Consider a reaction CH4 plus 2O2 giving CO2 and 2H2O. What is the stoichiometric ratio of CH4 to O2? So CH4 by O2 will be, so 1 mole of CH4 and 2 moles of O2 being reacted. So it will be 1 by 2. So 0.5. That is the correct answer. Next, consider a reaction. This is pentane C5H12 plus 8O2, 8 moles of O2 giving 5 moles of CO2 and 6 moles of H2O. Calculate this kilomole of CO2 produced per kilomole of C5H12 reacted. So from this equation, reaction equation, we can see that 5 moles of CO2 are produced when 1 mole of C5, C5H12 is being reacted with 8 moles of O2. So 5 by 1. So that will be the correct answer here. Any questions, anybody? Any questions? So if there are no questions, I'll go ahead and close this session for today. Thank you everybody for joining. Thank you everyone.